So here is how variation of parameters works. I'm going to explain the general method. Since the method is very long, there's going to be two parts in the video, but the general method is actually, the situation is not so bad because the general method produces some specific formula that can be then used just without repeating all the steps. Okay, so let me show you what I mean. So the first step of explanation of variation of parameters is, or whenever you want to do variation of parameters, the first step is always producing two linearly independent solutions of the corresponding homogeneous equation. Right? So I will do it y double prime plus 6y prime plus 9y. Our equation is equals t squared, but I will change t squared to 0. So that's the corresponding homogeneous equation. Alright, so now we need to set up the characteristic equation, which is r squared plus 6r plus 9. And now notice that this is a complete square. So this is r plus 3 squared, meaning that the corresponding characteristic equation only has one, the repeated root, which is minus 3. So the root is negative 3. The fact that the root is negative 3 means that the general solution of this homogeneous equation is a combination of e to the minus 3t and t times e to the minus 3t. So let me write them down. y1 is e to the minus 3t, and the other one is t e to the minus 3t. Well, the general solution of the homogeneous equation is going to be a combination e to the minus 3t times some coefficient plus t e to the minus 3t times some other coefficient. Right? So if we just wanted to solve the homogeneous equation, then we would stop here. But now we want to solve the non-homogeneous equation, which means that we need to find a particular solution of the non-homogeneous equation. Now to produce a particular solution of the non-homogeneous equation, as the name suggests, so variation of parameters. So the parameters that are present here are the coefficients in this form. So if I write C1 and C2, then these C1 and C2 are parameters. But to vary the parameters means that we change the constant parameters to some non-constant functions of t. So I will write u1 of t and u2 of t. And this is going to be the candidate for a particular solution. Right? So what we want then, we want to find a good combination of u1 and u2, so that when we substitute it back into the equation, then this y of t is going to satisfy the equation. In other words, we are looking for good forms of u1 and u2 such that y double prime plus 6y prime plus 9y equals t squared. So until now it's very easy to remember, right? So when you know the words variation of parameters, you can imagine what it means. But now we have the second step. Sorry. I don't know what happened. Okay, so let me write step 2. So step 2 is to calculate y double prime and y prime and y double prime, and then substitute them into the equation. But there is an extra trick, and the trick is actually very nice. So let me write down. So y is going to be e to the minus 3t times y u1 plus t e to the minus 3t u2. You need to remember that u1 and u2 are not constants but are functions of t. Then y prime equals, now I have to differentiate it according to the product rule. So I will do it like this. So first I will differentiate e to the minus 3t, but I am not going to calculate it. I'll just write e to the minus 3t prime u1 plus e to the minus 3t u1 prime. And here I will write t e to the minus 3t prime u2 plus t times e to the minus 3t times u2 prime. Wow, and now we have a very, very nice trick. So let me somehow emphasize that now we have a trick. So now the idea is that, well, we are looking for two unknown functions u1 and u2. So when we substitute u1 and u2 into the equation, so when we calculate y double prime and then equate the left hand side to the right hand side, we are going to get one equation on u1 and u2. But since we have two unknowns, then it means that we could come up with two equations and solve two equations. So where do we get the other equation? And the idea is that in order to kind of simplify everything, we are going to claim that this is going to be 0. We're going to require that this is 0. Okay? So in other words, we are not looking for just a random u1 and u2, but we want to look for particular nice combination of u1 and u2 so that this part is 0. Because if this part is 0, it means that our computation simplifies tremendously, right? We do not have to differentiate it again. And then we will write y double prime equals, we are going to differentiate these things again, e to the minus 3t double prime u1 plus e to the minus 3t prime u1 prime. So now I have differentiated this. Plus t e to the minus 3t double prime u2 plus t e to the minus 3t prime u2 prime. So now I have differentiated this part. Yeah, and there is, I forgot the plus sign here. Okay. So now I want to calculate I want to ensure that y double prime plus 6y prime plus 9y should be equal to t squared. So, but first let me calculate the left hand side. So the left hand side. So let me so y prime and y double prime are here, but it's going to be a bit tricky. So let me look at this column first. If we take y plus 6 times this part of y prime plus 9 this part of y, then, well, let me maybe write it here. then we're going to get u1 times e to the minus 3t double prime plus 6 e to the minus 3t prime plus 9 e to the minus 3t. But recall that e to the minus 3t is by construction a solution of the differential equation y double prime plus 6y prime plus 9y, which means that this thing is just 0, right? So this is 0 because it is by construction. So I will erase it. And write that this is 0. But then, because of exactly the same reason, y double prime plus 6y prime plus y, when you substitute everything and combine all the terms with u2, and again, since t times e to the minus 3t was by construction a solution of the differential equation y double prime plus 6y prime plus 9y, we're going to get 0 here too. Which means that the only thing that remains is, so there is nothing from y, there is nothing from y prime, there is just y double prime, and here we're going to get e to the minus 3t prime u1 prime plus t e to the minus 3t prime u2 prime, and this should be equal to, according to the original differential equation, to t squared. Alright, so let me quickly summarize it. So the main result of step 2, that if we want to find a particular solution of the non-homogeneous differential equation, then we can look for it in the form y1 times the first solution of the homogeneous equation plus u2 times another solution of the corresponding homogeneous equation, and these two functions u1 and u2 are supposed to satisfy certain extra conditions, right? And the extra conditions, the first extra condition is from the trig, and the second extra condition is from requiring the final result to be a solution of the original differential equation, right? So let me write, so we're looking for y of t in the form e to the 3t times u1 of t plus t e to the 3t u2 of t, where u1 and u2 satisfy the following two conditions. So the first condition is that if we just take e to the 3t and multiply by u1 prime plus t e to the 3t and multiply by u2 prime, this should be 0. And the second condition is that if we take the derivatives, e to the 3t prime u1 prime plus t e to the 3t derivative u2 prime, then we need to get the right hand side of the original differential equation, which is t squared. Well, but the nice thing about it is that this is actually a system of algebraic equations with unknowns u1 prime and u2 prime. Yes, so for every specific value of t, we get a system of algebraic equations on u1 prime and u2 prime. We can solve it, and then when we solve it, we get an expression for u1 prime and u2 prime. It is going to be a combination of, well, somehow some functions of t, and then if the original functions u1 and u2 can be recovered by integration. So that's how the method works. So, but of course, in order to ensure that the system of algebraic equations has a unique solution, we need to check that the determinant of the matrix of the coefficients, which here is e to the 3t, t e to the 3t, e to the 3t prime, and t e to the 3t prime, that this determinant is non-zero. But if you look at it, you will see that this is precisely the Wronskian of e to the 3t and t times e to the 3t, and the Wronskian of two linearly independent solutions of a second order differential equation is, of course, not going to be zero. So we had this theorem last week. So therefore we know for sure that this system of equations with unknowns u1 prime and u2 prime always has a unique solution. So the question is to find this solution. Okay, so now I'm going to stop now, and then I'm going to continue in the next part.